This is the Math 2 lesson summary video for the lesson entitled Extraneous Events. In Lesson 6 of Unit 6, Extraneous Events, the purpose of this lesson is for us to explore different ways to solve an inverse variation and square root equation. We discover in this lesson when extraneous solutions exist for a square root function. In the first part of this lesson, Extraneous Events, we are told that Jasmine, Kevin, and Francisco are working in a group and they were asked to solve the equation 2 divided by x equals 2x minus 3. Notice that the equation on the left-hand side is an inverse variation function in the form k over x, and the right-hand side is a line. We are asked to look at the three different methods that they used in order to solve this same equation, and then discuss their different methods. So in class, we discussed Jasmine's method first. We notice that the two equations are graphed on the same coordinate grid. So we see that 2 divided by x, or the inverse function, is graphed, and we also see that the line 2x minus 3 is graphed. So we do need to use our graphing calculator and graph these two. So we would type the left-hand side 2 divided by x and y1, and the right-hand side 2x minus 3 and y2, and we'd hit graph. Recall to find the intersection points between the red and the blue equations, we would go second, trace, number 5, intersect. It's asking us first curve to make sure we're on one side of the first curve, and we hit enter. Then it will jump automatically to the second curve, and it's going to calculate the intersection between those 2 points. So when I hit enter for a third time, I got the intersection point to be negative 0.5, comma, let me just make sure, looks like a decimal, comma, negative 4. Now notice in Jasmine's method, Jasmine did not include the y values. But when we're trying to find the intersection between these two equations, we do need to include the y values. So that is something that Jasmine is missing, but she did find the appropriate x values. So when we go back, let's check the other x intercept value. So number 5, I'm going to move my cursor to the other side of the graph, hit enter, it will jump to the second function, enter, and it says guess, and enter again. So my second solution to the inverse function and the line is 2, 1. So that was Jasmine's method for solving. Examining Kevin's method, it looks to us like Kevin used algebra and multiplied both sides by x first. So when we multiply by x, we know that those will cancel, and we'll just be left with 2 equals x times the quantity 2x minus 3. We can distribute the x, and we would get 2 equals 2x squared minus 3x. And subtract x, and we would get a nice quadratic equation, 2x squared minus 3x minus 2. Recall from Unit 4 that in order to solve or factor and then solve, we would need to factor 2x squared minus 3x minus 2. So 2x times x does give us 2x squared, and 1 times negative 2 does give us negative 2. If we redistributed that, we would get the original function. Therefore, our factors are 2x plus 1 times the quantity x minus 2. We would set each of our factors equal to 0, recall that from Unit 4, and solve for x. So we can see that indeed x equals negative 0.5 and x equals 2. So Kevin's method is solving algebraically. Let's take a look at Francisco's method. It looks like Francisco started off the same way as Kevin. Francisco multiplied both sides of the equation by x. The x's will cancel, so at that point he was left with 2 equals x times the quantity 2x minus 3. So Francisco brought everything to one side of the equation, so he had a quadratic equation, 2x squared minus 3x minus 2. This is where Francisco differs from Kevin. At this point, Francisco chose to graph the parabola and find the solutions instead of solve algebraically. So when we graph this parabola, we can use our graphing calculator. So Francisco typed into his y1 the equation 2x squared minus 3x minus 2. And at that point, he graphed his function to see where it crossed the x-axis. So we can see that we have two x-intercepts here and here. Recall the way to find those x-intercepts in our graphing calculator is we can use second trace, number 2, or zeros. Try that one more time, number 2. Left bound, we're going to go to the left of the x-axis, hit enter. Right bound, hit enter, and it's going to say guess. So it's telling us that one of the x-intercepts is negative 0.5. We can do the same thing for the other zero or root or x-intercept. We're going to move our cursor to the right-hand side so it's to the left of the x-axis and hit enter. We're going to move it to the right, enter, hit enter again. So our other zero is x equals 2. So notice that for all three of these individuals, they are getting the same x values. X equals negative 0.5 and x equals 2. In the next question, we are no longer given an inverse variation function and a line. We are given the equation 4x minus 2 equals the square root of x plus 3. So we can see that we are given both a line and a radical function, and we're asked to solve for x. So each of the three students still has their same method. Jasmine's method is to graph, Kevin's method is to use algebra to solve, and Francisco's method is to use a combination of algebra and graphing. So let's first take a look at Jasmine's method. She graphed both the line and the square root function in her graphing calculator and put it on a coordinate grid. So let's do that together. When we go to our y equals, we would type the left-hand side 4x minus 2 in our y1 and the right-hand side into y2, which is the square root of x plus 3. When we graph, Jasmine noticed there was an intersection between the blue line and the red square root function. So Jasmine wants to find that intersection point. Recall that we'll use the same function in our calculator, second, trace, and number 5, intersect. It's asking us to move the cursor to the first curve. Doesn't matter where as long as it's on one side, and we hit enter. It should jump automatically to the second curve. You can hit enter, guess, hit enter again, and it looks like the intersection is x equals 1. Now notice we're finding that x value there, so Jasmine got x equals 1. Let's move to Kevin's method. Kevin's method was to solve algebraically. So let's double check that Kevin gets the same answer as Jasmine using his method. In order to get rid of a square root in math, recall that we have to square both sides, and that's what Kevin did first. When Kevin squared both sides, he got 4x minus 2 times the quantity 4x minus 2, written twice, is equal to x plus 3, because the square and the square root cancel. He then distributed each of the values in his binomial in order to get the equation 16x squared minus 8x plus 4 equals x plus 3. He then combined like terms and subtracted x and subtracted 3 to get the quadratic function 16x squared minus 17x plus 1 equals 0. He then chose to factor, and he factored that into 16x minus 1 times the quantity x minus 1. Recall, once we get our factors to solve, then we set our factors equal to 0 and solve for x. So on this side, when Kevin solved, he got a value of x equals 1/16. And on the right side, Kevin got a value of x equals 1. But that's different than Jasmine. When we looked at the graph, we only saw one intersection point between the line and the radical function. So let's plug in these x values into the original equation and see if they check. So let's plug in the 1 first and double check that it works for our equation. 4 minus 2 is 2, and the square root of 4 is 2. So that one checks. Let's now check x equals 1/6. 4 times the quantity 1/6 minus 2 equals the square root of 1/6 plus 3. 4 times 1/6 is 4/6 or 2/3 minus 2 equals the square root of 1/6 plus 3. So I'll just take the square root of that. I got 3.4, and on the left side, when I subtract those two, I get negative 1.3. These are not equal. Therefore, we say that 1/6 x equals 1/6 is an extraneous solution. So let's talk a little bit about why x cannot be 1/6. Recall that the domain and range for a radical function is restricted. So to have a value of negative 1.3 here cannot be equal to the square root of x plus 3. This value can never be a range value for a radical function. If I go back to my graphing calculator and I take a look in my y equals, I just put in the radical function. Let's go to our table. Notice for your y values, are any of your y values negative? And they are not, because an answer to a square root function can never have an output or a range of a negative number. Therefore, whenever we are provided a radical equation, we must always check our solutions to make sure that they work. If they don't work, we say that our solution is extraneous. So let's take a look at our last example of Francisco's method. Again, Francisco uses a combination of algebra and graphing. Francisco did the first same part as Kevin, got it to be a quadratic function, and then graphed it. Notice here that Francisco got x equals 0.063, which was that x equals 1/6, and x equals 1. Recall we already know that x equals 1/6 will not check, so therefore it is extraneous. But let's take a look at the graph. I've already graphed my function, and I typed in my y equals 16x squared minus 17x plus 1. When I graphed it, I went to second trace and number 2, 0. I went left bound and right bound and hit enter. So checking that first one, we see that one solution for that parabola is 0.0625. But recall, anytime you're given a radical equation, you must plug in both of your x values to check your answer. So let's try a few examples where we're asked to solve and apply the methods that Jasmine, Kevin, and Francisco used to solve these problems. We are asked to identify extraneous solutions. So keep in mind, any equation that has a radical function could possibly have extraneous solutions. I'll highlight those because I see a radical function here, I see a radical function here, I see a radical function here, and a radical function here. So keep in mind, for any radical function, you have to check your solutions. I am going to start on number 2. So we are asked to just solve. And I'm just going to solve using Kevin's method, which is the algebra. So I'm going to multiply both sides by x. I'll get 3 on the right equals x times the quantity 3x plus 4.5. I'm going to distribute the x, and I will get 3x squared plus 4.5x equals 3. At this point, Kevin got all of his values to one side of the equal sign, so I'm going to subtract 3 and get 0. So on number 2, the best way to do this would be to use the quadratic formula. However, we could plug that in our graphing calculator to solve and find the x-intercepts. So now let's work with Francisco's method. Now that we have the quadratic equation, let's graph it and see what our x values are. So in our y equals, I typed in 3x squared plus 4.5x minus 3. I hit graph, and I'm going to use my 0 function, second trace number 2, to find the x-intercepts. So my first x-intercept here is the x value of -2. Second trace number 2, 0, and my second x-intercept is the value x equals 0.5. So we just use Francisco's method, a combination of algebra and graphing in order to find the x values. So my solutions for number 2 would be x equals -2 and x equals 0.5. Let's look at number 5, a square root function and a line. And let's use Kevin's method this time, where he's going to solve it algebraically. So we'll square both sides to start off with, and we'll get 3x plus 1 equals x plus 1 times the quantity x plus 1. When we distribute the right side, we will get 3x plus 1 equals x squared plus 2x plus 1. Combining our like terms by subtracting 3x and subtracting 1, we will get 0 equals x squared minus x, and those cancel. So in order to solve this, recall we need to take out the GCF, or greatest common factor, and divide both of these by the GCF. So we will get in parentheses x minus 1. At that point, we'll set both of our factors equal to 0 and solve. And we can see that our solutions here are x equals 1 and x equals 0. Remember that because we had a radical function, we do need to check both solutions. So let's do that now. Let's first check 0. The square root of 3 times 0 plus 1 needs to be equal to 0 plus 1. Well, this side will be 1. 3 times 0 is 0, and 0 plus 1 is 1. And the square root of 1 is 1. So 0 checks. Let's now check 1. The square root of 3 times 1 plus 1 needs to be equal to 1 plus 1, which is 2. 3 times 1 is 3, and 3 plus 1 is 4. The square root of 4 needs to be equal to 2. And we can see that 2 equals 2. Therefore, in this case, there are no extraneous solutions. If you need more help on the Ready, Set, Go homework for this task, please check the Canvas Student Support site.